Tonight, we turn to the story of a sideways world, a distant giant that spins unlike any other Uranus. Welcome to Orbit for Sleep. Let us trace the orbit of science and drift gently toward rest. You drift outward through the solar system, far beyond the warmth that shapes Earth's familiar rhythms. The light grows weaker, slower, less insistent. When Uranus finally comes into view, it does not present itself like the other planets. It appears tilted, almost resting on its side, rotating in a way that feels quietly unexpected. This sideways posture is not an illusion. Uranus truly spins, with its axis nearly horizontal compared to its path around the Sun. While most planets rotate like upright spinning tops, Uranus behaves more like a rolling wheel, turning as it travels. This single geometric difference reshapes everything about the planet, from its seasons to its internal balance. The reason this feels unsettling is rooted in everyday experience. On Earth, rotation feels stable because the planet's axis points in a consistent direction. Day follows night. Seasons change gradually. Even a spinning toy, when balanced, prefers an upright orientation. Uranus breaks that familiar rule. Its axis is tilted by about 98 degrees, meaning one hemisphere can face the sun continuously for decades, while the other remains in darkness. This unusual orientation was first recognized after Uranus was discovered in 1781, when astronomers began tracking the motion of its moons. The paths of those moons revealed the planet's true spin direction. Instead of orbiting above an equator aligned with the solar system, they traced a plane that confirmed Uranus was fundamentally misaligned. Scientifically, nothing about this rotation is wrong. Physics allows a planet to spin in any orientation as long as angular momentum is conserved. The idea of correctness comes from human habit, not cosmic law. Uranus simply preserves a history written into its motion. Something long ago altered its balance, and the planet has been calmly rotating that way ever since. On a cosmic scale, Uranus reminds you that stability is relative. What feels natural on Earth is not a requirement of the universe. Planets carry the memory of their formation in their movement. Uranus carries its memory sideways, slowly turning in the dark, unconcerned with expectation or symmetry. As Uranus continues its slow rotation, the true scale of its imbalance becomes clearer. The planet's axis is tilted by about 98 degrees relative to its orbit around the Sun. This means Uranus does not merely lean, it is almost completely turned onto its side. To understand this, it helps to return to something familiar. Earth's axis is tilted by about 23 degrees. That small angle is enough to create seasons, shifting sunlight north and south over the year. Uranus takes this idea to an extreme. Its poles, rather than its equator, spend long stretches facing directly toward or away from the Sun. As a result, a single season on Uranus lasts roughly 20 Earth years. During that time, one hemisphere experiences continuous daylight, while the opposite hemisphere remains in prolonged darkness. The transition between these states happens slowly, without sharp boundaries. Sunlight creeps across the planet over decades, reshaping atmospheric motion at a pace far removed from everyday human experience. This extreme tilt also changes how the planet distributes energy. Instead of sunlight warming a broad equatorial band, Heat arrives at steep angles, striking regions that are normally polar on other worlds. The atmosphere responds with subtle, large-scale movements rather than rapid storms. Everything unfolds gradually, as if the planet is reluctant to rush. The measurement of this tilt became reliable in the 19th century as telescopes improved and the orbits of Uranus's moons were mapped with greater precision. Their motion confirmed that the planet's rotation axis lies nearly in the plane of its orbit. What first appeared strange slowly resolved into a clear geometric fact. In physical terms, a 98-degree tilt is not unstable. Once established, a spinning body in space will keep its orientation unless acted upon by significant external forces. Uranus has been maintaining this posture for billions of years, quietly conserving the angular momentum it acquired early in its history. Seen this way, the tilt is not a temporary accident, but a defining feature. It shapes every long season, every atmospheric pattern, and every slow rotation. Uranus does not resist this configuration. It simply continues, turning sideways through the outer solar system, following the rules of motion with steady patience. As Uranus moves along its distant path, two motions unfold at once. One is rotation, the slow spinning of the planet around its own axis. The other is revolution, the long journey Uranus makes as it travels around the Sun. On most planets, these two emotions work together in a familiar way. On Uranus, they form an unusual relationship. Rotation describes how a planet turns in place. Revolution describes how it moves through space around a star. On Earth, the rotation axis stands mostly upright relative to the plane of revolution. This creates a predictable pattern of day and night, layered on top of steady, seasonal change. Uranus breaks this pattern not by changing how fast it spins, but by changing how that spin is oriented. Uranus completes one rotation in about 17 Earth hours. In that sense, it spins at a pace not very different from other large planets. The difference lies in direction. Because the axis is tilted almost sideways, each rotation rolls large regions of the planet in and out of sunlight very slowly, as Uranus continues its long revolution, which takes 84 Earth years. An everyday comparison helps clarify this motion. Imagine a rolling barrel moving down a gentle slope. The barrel rotates steadily, but the surface touching the ground changes in a way that depends on the direction of travel. Uranus behaves in a similar way. Its rotation is steady, but its orientation causes sunlight to interact with the surface and atmosphere in an unfamiliar rhythm. This distinction matters because seasons are shaped by revolution, not rotation alone. On Uranus, rotation determines the length of a day, while revolution determines which parts of the planet receive sunlight for decades at a time. The two motions are no longer neatly layered. They are intertwined. Astronomers recognized this relationship as observations improved in the 18th century and refined further in the 19th century. Tracking the planet's brightness over time revealed long-term changes that could not be explained by rotation speed alone. Only by considering the orientation of the axis relative to the orbit did the pattern make sense. In the wider context of planetary science, Uranus shows that rotation and revolution are independent variables. Their interaction can produce worlds that feel orderly, like Earth, or deeply unfamiliar, like this sideways planet. The laws governing both motions remain the same everywhere. What changes is how they are arranged in space. When Uranus is described as spinning the wrong way, the statement reflects human expectation rather than physical reality. In space, there is no preferred up or down, no universal orientation that defines what is correct. Motion follows rules, but direction itself carries no judgment. On Earth, rotation feels natural because it aligns with our daily experience. The sun rises, crosses the sky, and sets. Maps place north at the top. Spinning objects we use, from bicycle wheels to ceiling fans, are designed to behave in predictable orientations. These habits quietly shape how unfamiliar motion is interpreted. Uranus violates those habits, not the laws of physics. From a scientific standpoint, rotation is simply angular momentum conserved over time. A planet can rotate upright, sideways, or even upside down, as long as the total momentum remains consistent. Uranus satisfies this requirement perfectly. Its sideways spin is stable, persistent, and mathematically ordinary. An everyday example helps clarify this idea. Imagine floating in a swimming pool at night, far from walls or landmarks. If a ball drifts past while spinning, there is no obvious way to label its orientation. Without a reference frame, rotation loses its sense of right and wrong. Space behaves much the same way. Without a universal frame of reference, orientation becomes relative. The language of wrong entered popular descriptions as astronomers compared Uranus to other planets in the solar system. Most planets formed from the same rotating disk of material and ended up with similar axial orientations. Earth stands out because it preserves a different outcome of that early process. Difference, in this case, became mistaken for error. Historical records from the 18th century already hinted at this mismatch between expectation and observation. As Uranus's motion was measured more precisely, its unusual orientation forced astronomers to rethink assumptions about how planets should behave. The planet did not need correction. The framework used to describe it did. Seen clearly, Uranus does not spin incorrectly. It spins honestly, carrying forward the conditions that shaped it. The discomfort arises not from the motion itself, but from the limits of human intuition. When those limits loosen, the sideways world settles into place as one more valid expression of planetary motion. Uranus does not reveal its orientation all at once. From Earth, it appears as a small, distant disk, slow and faint against the background of stars. Its sideways nature became clear only through patience, repetition, and careful measurement over time. After Uranus was identified as a planet in 1781, astronomers began tracking its motion with increasing precision. Early observations focused on its position in the sky, confirming its long, slow revolution around the sunlight. The deeper insight came later, when its moons were discovered and their paths carefully mapped. Moons act as quiet indicators of a planet's rotation. They tend to orbit along a planet's equatorial plane, shaped by gravity over long periods. By observing the direction and tilt of these orbits, astronomers can infer how the planet itself is oriented in space. In the case of Uranus, Its largest moons followed a plane that was dramatically tilted relative to the solar system. This discovery unfolded gradually during the 19th century, as telescopes improved and observations became more consistent. Each new data point reinforced the same conclusion. Uranus was not simply tilted slightly. Its equator lay nearly vertical compared to its orbit, confirming a rotation axis unlike any other known planet at the time. There is an everyday parallel to this method. Imagine watching leaves floating on a slow-moving river at night. Even if the current itself is hard to see, the drifting leaves trace its direction. In the same way, Uranus's moons traced the invisible orientation of the planet beneath them. Later observations of Uranus's rings provided further confirmation. Like the moons, the rings aligned with the planet's equator. Their orientation matched the extreme tilt inferred from earlier measurements, reinforcing the geometric picture rather than changing it. Through these layered observations, astronomers did not impose a theory onto Uranus. They allowed motion to speak for itself. By listening to the quiet consistency of orbits, they uncovered the planet's sideways stars. The result was not a sudden revelation, but a slow accumulation of certainty, built from alignment, repetition, and time. Beneath Uranus's pale atmosphere lies a structure unlike that of rocky worlds or gas giants. Uranus belongs to a category known as ice giants, planets defined not by frozen surfaces, but by the materials that dominate their interiors. Water, ammonia, and methane exist there under pressures and temperatures so extreme that familiar states of matter no longer apply. From the outside, Uranus appears calm and uniform. Below the clouds, however, pressure rises rapidly. The upper atmosphere gives way to a dense mantle where these so-called ices are compressed into hot, fluid forms. They do not behave like ice cubes in a freezer. Instead, they flow slowly, carrying heat and electrical charge through the planet's interior. At the center lies a relatively small rocky core, comparable in size to Earth. Surrounding it is the thick mantle that makes Uranus an ice giant. This layered structure differs from Jupiter and Saturn, whose massive hydrogen envelopes dominate their internal makeup. Uranus is more compact, with its mass concentrated closer to the center. An everyday comparison helps ground this idea. Imagine a layered drink with heavy syrup at the bottom, thicker liquids above it, and lighter foam on top. Over time, the layers interact without fully mixing. Uranus's interior behaves in a similar way, with materials arranged by density and pressure rather than temperature alone. This internal arrangement plays a role in how the planet responds to its sideways orientation. Heat generated deep inside Uranus does not escape efficiently. Measurements made in the late 20th century revealed that Uranus emits far less internal heat than expected for a planet of its size. The reasons are still debated, but the layered structure likely slows the upward transport of energy. The unusual interior also influences the planet's magnetic field, which is offset and tilted relative to the rotation axis. Electrical currents flow through the fluid mantle rather than a simple central core. This creates a magnetic field that feels displaced and asymmetric, mirroring the planet's overall imbalance. In this way, Uranus's sideways rotation is not an isolated trait. It interacts quietly with the planet's interior, shaping how heat moves, how fields form. and how stability is maintained. The ice giant carries its history not only in its motion through space, but deep within its layered core. As Uranus turns through space, an invisible structure surrounds it, extending far beyond the visible planet. This is its magnetic field, a region shaped by moving electrical charges deep inside the planet. Unlike Earth's magnetic field, which aligns closely with its rotation axis, Uranus's field appears tilted, shifted, and quietly irregular. On Earth, the magnetic field emerges from a molten, metallic core spinning in a relatively symmetrical way. This symmetry keeps the field roughly centered and aligned. Uranus follows a different pattern. Its magnetic field is tilted by about 60 degrees relative to its rotation axis and is offset from the planet's center. The result is a field that wobbles through space as the planet rotates. This misalignment traces back to the ice giant interior. Instead of a simple, central dynamo, electrical currents likely flow through a shell of warm, electrically conductive fluids made of water and ammonia under extreme pressure. These materials move slowly and unevenly, generating magnetism away from the planet's geometric center. An everyday comparison helps clarify the effect. Imagine a flashlight held slightly off-center inside a rotating lantern. As the lantern turns, the beam sweeps unevenly across the room, changing shape and intensity. Uranus's magnetic field behaves in a similar way, creating a constantly shifting magnetic environment around the planet. This unusual field was measured directly during a spacecraft flyby in 1986, when instruments detected unexpected variations in magnetic strength and direction. The data confirmed that Uranus's magnetism does not sit neatly atop its rotation, but instead follows its own tilted geometry. The consequences extend far beyond the planet itself. Charged particles trapped in the magnetic field move along distorted paths, and the interaction between the field and the solar wind becomes complex and variable. The magnetosphere stretches, twists, and reforms as Uranus rotates, creating patterns unseen around more symmetrically aligned planets. Uranus's magnetic field reinforces a broader theme. The planet's sideways rotation, layered interior, and displaced magnetism are not separate oddities. They are interconnected expressions of the same underlying history. The field does not resist this imbalance. It adapts to it, quietly tracing the planet's unconventional structure through space. As Uranus continues its long journey around the Sun, time behaves differently on its surface. The planet's sideways orientation reshapes the meaning of seasons, stretching them far beyond anything experienced on Earth. Here, change does not arrive quickly. It unfolds over decades. Uranus completes one revolution around the Sun in 84 Earth years. Because its axis lies almost sideways, each hemisphere experiences prolonged periods of sunlight, followed by equally long periods of darkness. A single season lasts about 20 Earth years. During that time, the Sun barely moves in the sky, hovering near the horizon or remaining hidden entirely. On Earth, seasonal change is gradual but frequent. Clothing, agriculture, and daily routines adapt within months. Uranus offers no such rhythm. Entire generations of atmospheric motion develop under a single seasonal condition. When sunlight finally shifts, it does so slowly, giving the planet ample time to adjust. An everyday comparison helps frame this scale. Imagine living in a place where summer lasts 20 years, followed by 20 years of winter. The concept of transition would lose its sharpness. Instead of sudden change, there would be long periods of steady adjustment. Uranus exists in this extended state of balance. These extreme seasons influence the planet's atmosphere in subtle ways. Observations in the late 20th century revealed that cloud activity and wind patterns respond more to seasonal change than to daily heating. The atmosphere stores energy over long timescales, releasing it gradually as the angle of sunlight evolves. Because heat does not escape efficiently from Uranus's interior, sunlight becomes the dominant driver of atmospheric behavior. When a hemisphere emerges from decades of darkness, it warms slowly, altering circulation patterns across the planet. These changes are measured not in days or weeks, but in years. In this environment, seasons are not events. They are conditions. Uranus does not rush from one state to another. It remains steady, allowing time itself to stretch. The sideways world turns quietly, carrying each long season forward with deliberate patience. On Uranus, weather does not organize itself around an equator, warmed evenly by sunlight. The planet's sideways orientation reshapes how energy enters the atmosphere, and the result is a system of winds and clouds that behaves unlike anything on Earth. Because sunlight arrives at steep, shifting angles, heating is distributed unevenly across the planet for decades at a time. Instead of daily cycles driving convection, long seasons dominate atmospheric motion. Air masses respond slowly, adjusting to persistent conditions rather than rapid changes. On Earth, weather is powered by contrast. Warm air rises, cool air sinks, and rotating winds form as the planet spins. These processes happen quickly enough to feel dynamic and familiar. On Uranus, the contrasts are stretched across vast spans of time. The atmosphere settles into broad, stable patterns that can last for years. An everyday comparison helps clarify this difference. Imagine heating a room not with a flickering heater, but with a radiator that warms steadily for months. Air still moves, but gently and predictably. Uranus's atmosphere behaves in much the same way, favoring slow circulation over sudden storms. Observations made in the late 20th century and early 21st century revealed bands of clouds moving at different speeds and directions. Some winds reach impressive velocities, yet they flow smoothly without the violent turbulence seen on planets with stronger internal heat sources. The motion feels controlled rather than chaotic. The sideways seasons also influence where clouds form. Methane, which absorbs red light and gives Uranus its blue-green color, condenses differently depending on long-term sunlight exposure. This creates subtle changes in brightness and texture across the planet's surface, visible only through careful, patient observation. In this environment, weather becomes a slow conversation between sunlight and atmosphere. Uranus does not display dramatic outbursts. It maintains balance through steady motion, allowing its sideways orientation to guide winds and clouds into calm, enduring patterns. Deep inside Uranus, energy is generated slowly, left over from the planet's formation, and compressed by gravity over billions of years. On many planets, this internal heat rises and escapes, driving storms, winds, and visible activity. On Uranus, much of that heat remains quietly trapped. Measurements made during a spacecraft flyby in 1986 revealed something unexpected. Uranus emits almost the same amount of energy that it receives from the Sun. In contrast, planets like Jupiter and Saturn release far more internal heat than sunlight alone can explain. Uranus appears nearly balanced, as if its interior were holding its warmth close. This behavior is linked to the planet's layered interior. Heat must pass through thick regions of dense, sluggish material before reaching the surface. Instead of rising freely, energy moves slowly, diffusing rather than flowing. The result is a planet that looks calm, not because it lacks energy, but because that energy is reluctant to travel. An everyday comparison helps make this clear. Imagine a well-insulated house on a cold night. Even with warmth inside, little heat escapes to the outside air. From a distance, the house appears quiet and unchanged. Uranus behaves in a similar way, wrapped in layers that dampen outward motion. This trapped heat influences everything above it. With little internal energy feeding the atmosphere, sunlight becomes the primary driver of motion. Weather patterns remain smooth and long-lived. Sudden eruptions are rare. The planet's sideways seasons, rather than deep heat, shape its visible behavior. Scientists continue to debate why Uranus retains its heat so effectively. Some models suggest that early events disrupted the normal flow of energy, locking the interior into a stable configuration. Others point to compositional layering that resists mixing. What remains clear is the outcome, a world where energy moves slowly and deliberately. In this quiet balance, Uranus completes the picture formed by its tilt, its interior, and its atmosphere. The planet does not broadcast its power outward. It keeps it contained, allowing time and orientation, rather than force, to define its character. Compared to Uranus, Earth appears almost perfectly upright. Our planet's rotation axis is tilted by about 23 degrees, a modest angle that produces gentle, predictable seasons. This small inclination has shaped the rhythms of life in quiet but profound ways. Because Earth's tilt is limited, sunlight shifts gradually between hemispheres over the course of a year. No region remains locked in continuous daylight or darkness for decades. Instead, day and night alternate reliably, and seasonal changes arrive with a steady cadence. This regularity allows ecosystems to anticipate change rather than endure extremes. An everyday example makes this difference clear. Imagine adjusting a desk lamp slightly to one side. The light spreads unevenly, but the room remains usable and familiar. Tilting the lamp completely onto its side, however, floods one area while leaving another in shadow. Earth's tilt resembles the first case, while Uranus represents the second. This mild orientation supports biological timing. Plants synchronize growth with seasonal light. Animals migrate, hibernate, or reproduce according to predictable cycles. Human societies, from early agriculture to modern calendars, developed around the expectation that seasons would return in recognizable patterns. Astronomers in the 17th century began to understand Earth's axial tilt as the true cause of seasons, replacing older ideas that relied on distance from the sun alone. This insight revealed how sensitive planetary environments are to even small geometric differences. Earth's tilt has also remained relatively stable over long periods. Interactions with the Moon help prevent large swings in orientation, preserving a climate that changes slowly rather than abruptly. This stability contrasts sharply with Uranus, whose extreme tilt reshapes its entire planetary system. Seen alongside Uranus, Earth's orientation appears not inevitable, but fortunate. A modest tilt creates balance rather than drama. It allows time to flow in manageable cycles, supporting life and civilization without demanding constant adaptation. In the vast range of planetary possibilities, Earth occupies a narrow and quietly supportive zone. If Earth's axis were suddenly tilted to match Uranus, the familiar structure of seasons would dissolve. The change would not arrive as a dramatic event, but as a slow reshaping of light, temperature, and time. Geography would begin to matter less than orientation. With an extreme tilt, one hemisphere would face the sun continuously for many years, while the other would remain in prolonged darkness. Day and night would lose their regular alternation. Instead of mornings and evenings, there would be long intervals of persistent light or extended night. An everyday comparison helps make this shift concrete. Imagine living in a city where the sun rises once and does not set for decades, followed by an equally long absence of daylight. Clocks would still mark hours, but the connection between time and light would weaken. Daily routines would detach from the sky. Temperature patterns would follow the same slow rhythm. Regions exposed to constant sunlight would warm steadily, not sharply, while areas in darkness would cool over many years. Seasonal contrast would deepen, but transitions would stretch across generations rather than months. Ecosystems would struggle to adapt. Plants depend on reliable light cycles to regulate growth and reproduction. Animals rely on seasonal cues for migration and breeding. With decades-long seasons, many of these biological signals would disappear or arrive too late to be useful. Human civilization would face similar challenges. Agriculture, infrastructure, and energy use are built around predictable seasonal timing. Extended periods of light or darkness would force societies to redesign how food is grown, how cities are heated or cooled, and how work aligns with the natural environment. In this imagined scenario, Earth would not become uninhabitable immediately. Instead, it would become demanding. Life would persist, but only through constant adjustment. The exercise reveals how deeply Earth's mild tilt supports stability, not by eliminating change, but by pacing it within human and biological limits. A planet's ability to support life depends less on dramatic features and more on quiet consistency. Habitability is shaped by how stable conditions remain over long periods, allowing complex systems to adapt rather than constantly react. Axial tilt plays a subtle but central role in this balance. When a planet's orientation is stable, energy from its star is delivered in a predictable pattern. Temperatures fluctuate within limits, seasons repeat with recognizable timing, and ecosystems can synchronize growth, reproduction, and rest. Stability does not mean sameness. It means change arrives at a pace life can absorb. An everyday comparison helps clarify this idea. Consider a steady work schedule versus one that shifts unpredictably every few weeks. Productivity and health are easier to maintain under regular patterns. In the same way, biological systems depend on reliable environmental rhythms. Uranus illustrates the opposite condition. Its extreme tilt produces environments that remain locked in one state for decades, followed by long transitions into another. Such persistence limits the range of life strategies that could function there. Adaptation would require endurance rather than flexibility. Earth occupies a narrow middle ground. Its axial tilt introduces seasonal variety without overwhelming continuity. Combined with a stable orbit and moderating influences such as the Moon, this geometry supports long-term climate patterns that change gradually rather than abruptly. Astronomers studying exoplanets often use axial tilt as one of several indicators when assessing potential habitability. A planet may lie within a star's habitable zone, yet still experience conditions too extreme or irregular for life to develop complexity. Geometry, not distance alone, shapes the outcome. Seen through this lens, habitability is not a single trait, but an emergent property. It arises from stability layered over time. Uranus and Earth represent different solutions to planetary motion, reminding us that life favors worlds where change is measured, not relentless. Human civilization developed within a narrow range of environmental regularity. Long before technology softened the impact of climate, societies learned to align daily life with repeating natural cycles. Predictability, more than abundance, allowed planning to replace reaction. On Earth, the steady return of seasons shaped agriculture. Planting and harvest followed familiar patterns passed down across generations. Even when weather varied, the broader rhythm remained intact. This reliability made surplus possible, and surplus supported cities, trade, and written record. An everyday comparison helps illustrate this dependence. Consider living in a place where electricity turns on and off at random intervals lasting months. Daily routines would become difficult to maintain, not because power is absent, but because its timing cannot be trusted. Civilization faces a similar challenge without predictable environmental cycles. Axial tilt plays a quiet role in this stability. Earth's moderate tilt ensures that changes in temperature and daylight arrive gradually. Societies have time to adapt infrastructure, food systems, and labor patterns to seasonal shifts. Extreme or irregular cycles compress this margin for adjustment. On a planet with decades-long seasons, human systems would struggle to synchronize. Education, construction, and agriculture depend on shared expectations of time. When environmental conditions persist too long or change too slowly, coordination becomes difficult. Planning horizons stretch beyond individual lifetimes. Historical records from the early development of agriculture in the 10th millennium BCE already reflect this relationship between seasonal predictability and settlement. Permanent communities formed where cycles could be anticipated, not merely endured. Seen in contrast with Uranus, Earth's gentle rhythm appears foundational rather than incidental. Civilization does not require perfect conditions. It requires conditions that repeat. Predictable cycles allow knowledge to accumulate, institutions to stabilize, and culture to persist across time. Uranus is often described as an oddity, a planet that somehow escaped the rules followed by the rest of the solar system. Seen more carefully, it serves a different role. It acts as a reminder that planetary systems do not converge on a single outcome. They preserve the full range of possibilities allowed by physics. The solar system appears orderly, largely because its major planets share a common origin. They formed from a rotating disk of gas and dust, inheriting similar directions of motion. Uranus emerged from this same environment, yet carries evidence that early conditions were not perfectly uniform. Its sideways orientation reflects a path that diverged, not one that failed. An everyday comparison helps ground this idea. Imagine several clocks built from the same design, all keeping time accurately, yet mounted at different angles on a wall. Each functions correctly, but one draws attention, simply because it does not match expectation. Uranus attracts focus for the same reason. In planetary science, such differences are valuable rather than inconvenient. They preserve information about early events that smoother systems erase. Uranus retains the imprint of disturbance, whether through collision, migration, or internal reorganization. The planet did not recover into symmetry, it remembered. This perspective reshapes how worlds are evaluated. Instead of treating Uranus as a rare anomaly, it becomes a caution against assuming regularity. The apparent calm of Earth-like conditions is not guaranteed by formation alone. Stability emerges from a narrow set of circumstances. As astronomers discover planets around other stars, extreme tilts and irregular rotations appear increasingly common. Uranus no longer stands alone. It becomes a local example of a broader cosmic pattern, one in which variation is the norm. In this light, Uranus is not an exception to be explained away. It is a warning written in motion. Planetary systems can settle into many configurations, and the familiar arrangement that supports life on Earth represents only one quiet solution among countless alternatives. Long before Uranus settled into its present rhythm, the young solar system was a crowded and unstable place. Newly formed planets shared space with large remnants of rock and ice, moving along intersecting paths. In this environment, collisions were not rare interruptions. They were part of the process. The giant impact hypothesis suggests that Uranus's extreme tilt was established by a massive collision early in its history. A body several times the mass of Earth may have struck Uranus at an oblique angle, transferring angular momentum and forcing the planet's rotation axis to tip dramatically. The impact did not shatter the planet. It redirected it. An everyday comparison helps make this idea tangible. Imagine a spinning bowling ball gently nudged from the side by a heavy object. The ball continues to spin, but its orientation changes. The motion remains smooth, yet the axis no longer points where it once did. Uranus behaves in much the same way, preserving rotation while altering direction. Computer simulations developed in the late 20th century showed that such an impact could reproduce Uranus's current tilt without destroying its structure. These models also explain why the planet retained a system of moons and rings aligned with its new equator. The collision reshaped the system, then allowed it to settle. This hypothesis helps clarify other features as well. A violent early event could have disrupted internal heat transport, contributing to Uranus's unusually low heat output today. It may also explain the layered interior that resists mixing, locking energy deep within the planet. The giant impact hypothesis does not describe a single moment frozen in time. It describes a transition. After the collision, Uranus gradually stabilized, conserving the angular momentum it had gained. Over millions of years, the planet cooled, rotated, and refined its sideways posture. Seen at this scale, Uranus's orientation is not mysterious. It is historical. The planet carries the memory of an early encounter, written into its rotation. The sideways world turns as it does because the solar system once allowed violence and then moved on. Uranus once appeared unique because it was the only sideways world we could observe closely. As astronomy extended beyond the solar system, that sense of isolation faded. Planets orbiting other stars began to reveal a wide range of orientations, many far more extreme than those found at home. These distant worlds, known as exoplanets, are often detected indirectly through subtle changes in starlight. By measuring how planets transit their stars or tug on them gravitationally, astronomers infer orbital paths, rotation rates, and, in some cases, axial tilt. The results point to diversity rather than uniformity. Some exoplanets orbit at steep angles relative to their star's rotation. Others move along paths that appear tilted or even reversed. In tightly packed systems, gravitational interactions between planets can slowly tip axes over time. In more chaotic environments, early collisions leave permanent marks on orientation. An everyday comparison helps clarify this range. Imagine a group of spinning tops set on a gently shaking table. Some remain upright, others wobble, and a few settle into unexpected angles. Each follows the same physical rules, yet small differences in interaction produce lasting variation. Observations made in the early 21st century confirmed that extreme tilts are not rare. Hot giant planets orbiting close to their stars often show misaligned motion, suggesting turbulent formation histories. These findings reshaped expectations about what planetary systems typically look like. In this broader context, Uranus becomes familiar rather than strange. Its sideways rotation fits naturally into a spectrum of outcomes shaped by gravity, collision, and time. What once seemed like an exception now appears as one local expression of a universal process. By studying tilted worlds beyond the solar system, astronomers gain perspective on their own. The lesson is quiet, but persistent. Planets do not aim for symmetry. They inherit it, or they do not, depending on the paths they travel early on. In everyday language, the word wrong suggests deviation from a standard. In the universe, standards are local, temporary, and often accidental. When planetary motion is examined across many systems, what appears incorrect usually reflects expectation rather than error. Physical laws describe how matter and energy behave, but they do not prescribe outcomes. Gravity allows countless orbital arrangements. Rotation can settle into many orientations. As long as energy and momentum are conserved, motion remains valid. The universe does not rank configurations. It permits them. An everyday comparison helps ground this idea. Consider handwriting styles. Letters remain readable across many forms, despite variations in slant, spacing, or shape. None are wrong. They simply reflect different conditions of learning and habit. Planetary systems exhibit the same diversity of expression. Uranus highlights this distinction clearly. Its sideways rotation feels unusual only because nearby planets share a similar alignment. If the solar system were filled with tilted worlds, Uranus would blend into the background. Context creates judgment. Astronomical surveys conducted in the early 21st century revealed that irregular orbits, extreme tilts, and unexpected motions are common around other stars. Symmetry, once assumed typical, now appears selective. Order exists, but it is not uniform. This realization reshapes interpretation. Instead of asking why a planet behaves incorrectly, astronomers examine how it arrived at its present state. History replaces judgment. Motion becomes a record rather than a mistake. In this broader view, wrong loses meaning. The universe does not correct itself toward ideal forms. It accumulates outcomes. Each planet turns according to its past, carrying forward a configuration that is neither flawed nor exceptional, but simply allowed. For decades, Uranus has remained largely unexplored, observed mostly from afar. The most detailed information still comes from a single spacecraft flyby, when a probe passed the planet briefly and continued onward. Since then, understanding has advanced through telescopes, models, and inference, rather than direct presence. Future missions aim to change this perspective. Scientists have proposed sending an orbiter to Uranus, designed to remain in the system for years rather than hours. Such a mission would allow continuous observation of the planet's atmosphere, magnetic field, rings, and moons across changing seasons. The value of long-term study is easy to grasp through everyday experience. Watching a place for a single afternoon reveals little about how it changes. Living there for years exposes patterns that short visits miss. Uranus requires patience of this kind. Its slow seasons and subtle shifts demand extended attention. An orbiter could trace how sunlight gradually reshapes weather systems, how the tilted magnetic field evolves as the planet rotates, and how internal heat interacts with long-term atmospheric motion. Instruments could sample particles in the magnetosphere, mapping a structure that twists differently from any other known planet. The moons of Uranus are also of growing interest. Many show signs of complex geology shaped by the planet's unusual orientation and gravitational environment. Studying them could reveal how sideways rotation influences the evolution of entire planetary systems, not just the central world. Proposals developed in the early 21st century emphasize this broader context. Uranus is no longer viewed as a distant curiosity, but as a key example of planetary diversity. Exploring it directly would refine models used to interpret countless exoplanets discovered around other stars. Future missions to Uranus represent a shift in approach. Instead of brief encounters, they favor sustained observation. In doing so, they acknowledge the planet's defining trait. A sideways world reveals its nature slowly, and understanding it requires time spent turning alongside it. When viewed from a distance, the universe does not favor a single arrangement. It allows matter to move, rotate, collide, and settle in countless configurations. Planets spin upright, tilted, inverted, or sideways, each following the same physical laws while arriving at different outcomes. Rotation is shaped by history rather than intention. Early collisions, Gradual gravitational interactions and internal rearrangements leave lasting marks on orientation. Once established, these motions persist, conserved over immense spans of time. The universe does not revise them toward symmetry. It preserves them as records of what's occurred. An everyday comparison helps ground this idea. Consider a collection of wind chimes hanging from the same frame. Each responds to the same breeze, yet no two move in exactly the same way. Their motion reflects subtle differences in shape, balance, and interaction. Planetary rotation emerges from a similar interplay. Uranus illustrates this freedom clearly. Its sideways spin does not challenge physical law. It demonstrates the range permitted by it. The planet turns calmly, unconcerned with comparison, carrying forward a configuration shaped by chance and time. Across the galaxy, planets repeat this pattern in varied forms. Some rotate rapidly, others slowly. Some align neatly with their orbits. Others diverge sharply. None violate the rules that govern motion. They simply occupy different points within the allowed space of possibility. This perspective reframes how planetary systems are understood. Order is not uniformity. Stability does not require sameness. The universe remains coherent, not because everything behaves alike, but because all motion obeys the same underlying principles. In this broader view, Uranus is neither strange nor instructive alone. It is one example among many, quietly demonstrating that the universe accommodates difference without disruption. Worlds turn as they must, each in its own way, within a cosmos generous enough to allow many ways to spin.